Okay, so welcome everyone to one of our new online seminars. Today we're very happy to have Suvrat Raju from ICTS, who's going to tell us about a canonical view on holography. So Suvrat, please take it away.
Okay, so thank you very much for having me over for this seminar, and thank you very much for all of you who've joined. I hope all of you are staying safe. So I must admit I'm still a bit of a novice at doing these kinds of seminars, so I hope things work well. But you know, if there's some technical problem and you can't understand, please stop me and I'll be happy to go over things again. So this is work that's based on a number of papers. I'm going to talk mostly about the last paper on this list, which is a paper we wrote a couple of months ago with Alok, Siddharth, and Pushkal. But in a sense, it goes back to work done over several years, including earlier work with Shovik, Jan, and Kyriakos. Before I start the bulk of my talk, let me just try and explain the main point that I would like to make. So if I'd like to communicate one thing in this talk, it would be as follows. So when we think about holography, and if you think about the extrapolate dictionary in holography, which tells us in particular that if you look at the boundary limits of bulk operators, those are boundary operators, then it tells us, gives us the following picture for how quantum information is stored in quantum gravity. And it's a very unusual picture. And what it says is that in quantum gravity, if you specify the wave function of a system everywhere outside a bounded region, you also specify it completely inside that region. So this, from the point of view of a local quantum field theory, of course, is a very unusual feature, because you might have expected in a local quantum field theory to be able to specify the wave function independently outside and inside. But what I'm going to try and persuade you is that in quantum gravity, this is not possible. And this, in a sense, is the main aspect of holography that I'm going to address. So I'm going to try and establish a picture of this sort for four-dimensional asymptotically flat spacetimes. Before that, I'll review how a picture of this sort is also consistent with what we understand from ADS-CFT. And the strategy I'd like to keep in this talk, and the philosophy of what I'm going to say is the following. Throughout this talk, I'm going to use only semi-classical considerations, but I'm going to supplement them with what I think are reasonable assumptions about the ultraviolet theory. So at no point in this talk am I going to try and claim that, you know, the semi-classical theory is a complete theory. Of course, we need a more complete theory, which comes from string theory or a CFT or something else. But I am nevertheless going to use semi-classical considerations and then argue for some reasonable extrapolations to the UV theory. And everything I derive will come from that. And as I said, the main result I'd like to establish is this result about how quantum information is stored. In particular, that in quantum gravity, if you specify the state of the universe outside a bounded region, everywhere outside, you also specify it inside the region. I'm going to discuss the implications of this result for black holes. And a simple way of saying what the implication is that I'm going to argue that this picture implies that information never goes in and comes out of a black hole, but in a sense, the information is always outside. If one accepts this result, then many versions of the information paradox can be resolved, and I'll try and explain how that happens at the end of the talk. So this is an outline of what I'm going to say. I already did most of the introduction. I'm actually going to spend a significant part of my time trying to establish this picture I described in asymptotically ADS spacetimes. Not because that's the main result of our paper, but because a lot of the technical aspects can be brought out in a simple way if one considers asymptotically ADS spacetimes, and where one thinks one understands quantum gravity well using ADS-CFT. That's my section 2. And if you look at the paper, that's appendix A in the paper. And then I'll describe how one can generalize these results from ADS spacetimes to asymptotically flat spacetimes. And then, as promised, I'll discuss the implications for the information paradox. So the copy of the outline is also on the left part, as you can see. So as I said, let me start by discussing how one might establish this picture of holography using semi-classical considerations in asymptotically ADS spacetimes. So I'm going to consider spacetimes that are globally anti-de Sitter. So just to set notation, I have this r coordinate that goes to infinity, and then there are some subleading fluctuations of the metric that indicate deviations from global ADS, and we'll choose the standard Pfefferman-Graham gauge. So we set the radial component HR mu to 0, and then we have some fall off for the other components of the metric. Okay. Now, the first question you'd like to ask in the semi-classical canonical theory is what are the good observables in a theory of gravity? And of course, the good physical observables are those that are invariant under small diffeomorphisms. So they don't have to be invariant under large diffeomorphisms because we allow those are physical transformations, but they do have to be invariant under small diffeomorphisms. And in particular, an interesting class of physical observables in the canonical theory is comprised just of the subleading terms in the metric or in other fields near the boundary. So as I said in the previous slide, you put some fall-off conditions on the metric. These are what are called normalizable fall-off conditions. And then you just pick off the coefficient of the r to the d minus 2 fall-off. And I'm going to call that Tij. This is what, of course, becomes the stress tensor in ADS CFT, but I'm not using that here. Or else you might have some scalar field with some mass, and you pick off the coefficient of the r to the delta fall-off, and that's a variable I'll call O5. So these variables T and O are good observables in the canonical theory as well. Now I'm going to be interested in the algebra that's formed by these observables. So I would like to consider not only measuring one-point functions of these observables, but also measuring arbitrary polynomials of these observables. And of course, this is the way one usually formulates a quantum field theory. One has some set of operators, and then one considers the algebra of that set of operators. So in particular, I want to consider the algebra of observables formed by taking these boundary values of these bulk fields that I described and taking them in a small time band 0 to epsilon. So you should think of these as, bulk observables pushed off to the boundary, but then restricted to a small time band. So if you look at the picture on your screen, you see that small red time strip. It has a very small thickness, which is 0 to epsilon. The epsilon is important for me, the fact that it's not 0. And then I consider all polynomials of these boundary or these boundary limits of bulk observables in this time band. And that is what I will call the boundary algebra. So I emphasize the boundary algebra right now is not the set of all observables everywhere at all times on the boundary, but just the set of observables in this limited time from 0 to epsilon. Okay, so now what is the result I'd like to establish in anti-de Sitter space? The result I'd like to establish is as follows. Let's say we have two bulk states, and those two bulk states are distinct. Then I claim that they can be distinguished by observables in this boundary algebra. So on your screen, you see two bulk states, two pictures of hypothetical wave functions in anti-de Sitter space. One picture differs from the other in that it has this small blue bump in the middle near the center of ADS. And what I'm going to try and establish is that if you carefully consider the canonical theory of gravity, then by making observations in this red strip, you can determine whether the blue bump exists or doesn't exist. And of course, this would be a false statement if you didn't have gravity. In a local quantum field theory, the observables that create the blue bump commute with all observables that live near the red strip. And so this is an unusual feature of quantum gravity that I would like to establish from semi-classical considerations. Okay, so I need to make some assumptions when I do this. So I'm going to try and articulate my assumptions as precisely as possible. And so I'll have 2 or 3 assumptions, and then I'll try and draw conclusions from them. So the first assumption I'm going to need to establish this result.
Suvrat,
yes.
Just to clarify, what are you assuming about the sources as a function of time on the boundary? Like in your
right now, I
metric,
haven't said anything about the sources. This is just a wave function on ADS. So you could specify. You can think of this as initial data if you like. So you could specify a wave function like the picture on the left or the picture on the right. These are 2 states of the theory on ADS. And the claim is I can determine which state it is by making observations in the red time band.
No, I agree with that. I'm asking, in a general ADS-CFT setup, we could turn on sources as we go forwards in time, right? And
good.
Independent information.
Thank you. So I'm only going to consider normalizable fluctuations. So the sources are just set to 0. So I'll allow you whatever state you like in the bulk. So you can have in the bulk theory, you can specify whatever initial data you like, and then that just evolves without turning on any sources. So that was the setup in the beginning, that I allow only normalizable fluctuations. So
okay,
I'm not going to disturb the theory from outside.
Right, but that's not the most general thing we can do in ADS-CFT.
Well, you could do more general things. You could turn on sources, and then then you have to think of an external observer who turns on those sources. So
right.
I want to think of a self-contained theory where you specified some initial data, and then you allowed the cosmos to evolve in whatever initial data you specified. For instance, if you think of flat space, you specify some initial data at scry minus, and you allow it to evolve up to scry plus. So that's the same kind of setting I want to consider.
I understand. The reason I'm sort of pushing this a little bit is because in ADS, we know that the usual boundary value problem in gravity is different, right? Even to specify a classical evolution, we need to specify data on the time-like boundary.
Yeah, so I specified data by saying that we don't have sources. So I'm not going to allow external observers to come and interfere with the system. If you allow external, we could do that. We could try and allow like external observers to come and interfere with the system. But then it's clear, then you have more complications. I mean, I don't think there's by the way, if you allowed external observers to interfere with the system, then in any case, the boundary observer can detect that. So the interesting thing I want to emphasize here is that you're just given a time slice, and you might have thought that these two states are indistinguishable from the red band, but they are distinguishable in gravity. I mean, that's the interesting thing that I would like to emphasize. So sources are kind of peripheral to this aspect that I want to emphasize.
Okay, thanks.
Okay. Okay. Fine. So now the assumption I want to make, the first assumption is as follows. From the semi-classical theory in global ADS, we know something about the low energy structure. And what we know about the low energy structure is that the vacuum is unique, and it's separated by a gap from the lowest excited state. The precise value of the gap depends on the spectrum of massive particles. The graviton itself has an energy D in ADS units. But I don't need that. What I would like to assume, as I said, I'll make some statements about the semi-classical theory and then assume something about the UV theory. What I would like to assume is that in the ultraviolet theory, in the full theory of quantum gravity, whatever that is, the vacuum remains unique. So, some of these excited states don't descend and don't make the vacuum degenerates. Okay, so that's an assumption that I would like to make. And that's the statement that the canonical theory or the semi-classical theory gives you a good picture of the low energy physics of the system. Okay, so this is just an assumption about the low energy theory. The low energy theory, in the full theory, the vacuum will remain unique. Okay. The second statement, this is again a statement about the semi-classical theory. In the semi-classical theory, the Hamiltonian of the theory is a boundary term. And this is a direct result of imposing invariance under small diffeomorphisms on the wave function. So if you do the Wheeler-de Wit quantization of gravity in ADS, then the Hamiltonian is a boundary term. But it's something that's pretty familiar to us in any case, just from the Gauss law. It's the fact that you can determine the energy of the state inside just by making observations near infinity. And provided you... Is there a question?
Yes, we have a question from Daniele.
Yeah, hi, just to clarify. So the vacuum you were talking about in the previous slide is the ground state for this boundary Hamiltonian. Is that correct?
Yes, that is correct.
Okay, thanks.
And provided we regulate the theory in a way that respects diffeomorphism invariance, they say it will remain a boundary term. Now, I don't want to assume that this boundary term is the Hamiltonian of the full theory of quantum gravity. Okay? But what I do want to assume is that the vacuum of this operator H that I wrote down previously coincides with the vacuum of the full theory, and that this operator H remains a positive operator. So this is the statement that if you were to make this measurement of the metric at infinity and you find that that answer is 0, then you know that you're an empty ADS, you're in the vacuum. So this is once again a statement about low energies. It's the statement that this boundary operator correctly identifies the low energy structure of the theory. In particular, it may be that when you look at the CFT, HCFT and this H fail to coincide when you look at black holes or very highly excited states. And, there are microstates which are exponentially small, separated by exponentially small gaps. But the assumption here is an assumption about low energy, and it's that this H identifies for you correctly the vacuum of the theory. Okay, now this H that I wrote down, this boundary operator, which you could define in the time at time 0, it lives in what I was calling the boundary algebra, this A boundary. And it's a standard property of operator algebras that if an operator belongs to an algebra, then all its spectral projectors also belong to the algebra. In particular, I'm interested in the projector onto the ground state of this H, which is what I'm calling P omega. And because H belongs to this boundary algebra, this P omega belongs to this boundary algebra. And by the first assumption I made about the vacuum structure of the theory, this P omega is a one-dimensional projector. Okay, so now I want to make a third assumption. This is an assumption about the Hilbert space. So I'm going to assume that the full theory can be formulated in the following Hilbert space. You start with the vacuum in the far past at minus infinity, and then you excite the vacuum by acting with operators near the boundary at all possible times. So it's important that these operators are not restricted to what I call a boundary, in that you don't have to act in the time 0 to epsilon. Rather, I'm going to allow you to act with operators all the way from minus infinity to whatever time you like. And I'm going to consider the set of states that you got in this fashion. So in particular, physically, this corresponds to what you would get by starting with the vacuum and throwing in stuff from the boundary. Now, why is this a good assumption? Why is it good to say that the theory can be formulated in this way? This is a good assumption because you see that under time evolution, this Hilbert space that I have written down is manifestly closed. And that's because when you do time evolution with the full Hamiltonian of the theory, you just switch around the values of these TIs. If you do time evolution, you take a state of this kind and you evolve it with time, you'll just change the values of the T's. And therefore, you will get another state that belongs to this Hilbert space. And therefore, considerations of unitarity alone cannot force us to include additional states. The second reason this is a good assumption is that this Hilbert space is actually quite large. I mean, this accommodates all black holes that you can form from collapse by throwing in matter from the boundary. And so it's an interesting Hilbert space. It may be possible to formulate the bulk theory in a larger Hilbert space, which consists of other states, but then my arguments that follow won't hold. And therefore, I'm going to formulate the bulk theory in this Hilbert space, which, as I said, is a super selection sector in that it's closed under time evolution. And it's interesting super selection sector in that it involves a lot of interesting dynamics, including black holes that can be formed from collapse. Okay, so now I want to establish a preliminary result. The preliminary result is as follows. I just told you in the previous slide that I was considering the Hilbert space that you would get by acting with operators at all values of time on the vacuum. But now I want to tell you that this Hilbert space is in fact the same as the Hilbert space that you would get by acting with operators in the time 0 to epsilon. More precisely, any vector in the larger Hilbert space can be approximated arbitrarily well by a vector that you would get by acting with just operators in the time band 0 to epsilon on the vacuum. Okay, so this is a preliminary result that I would like to establish. And we can establish it as follows. Let's establish it by contradiction. Let's say there was some state that belonged to the Hilbert space I described, which was formed by acting with all operators at all values of time. But it can't be formed by acting with operators in the time band 0 to epsilon. Then think about this function f of ti that is on the screen. This function f of ti, which is the inner product of this state psi with some other state that's formed by acting with operators in the time period 0 to epsilon, is 0. And that's because by assumption, we assume that this state couldn't be created by acting with operators in the small time band on the vacuum. But now we can insert a complete set of energy eigenstates in between all of these operators Ti's of Tn. And if you assume that the full Hamiltonian has a property of positivity, then you will see that this function f of Ti is analytic when these variables T1, these time differences are continued in the upper half plane. So now there's a theorem in complex analysis that tells you that if this f vanishes for Ti real in some finite domain, then this f must vanish everywhere. Okay. But that's impossible because we assume that the state psi was created by acting with some polynomial of the kind on the screen, except that it had values of T that were maybe outside the range 0 to epsilon. So it cannot be that this f of Ti vanishes for all real Ti. And therefore we've reached a contradiction with our initial assumptions. And therefore there is no state that is orthogonal to all states that can be created by acting with operators in the band 0 to epsilon. Okay. So what I proved right now is that if, yes.
Here you mean positivity of the full quantum Hamiltonian, or just positivity of A?
Positivity of the full quantum Hamiltonian.
Okay.
Is what I assumed here. Because these operators evolve according to the full quantum Hamiltonian.
Yes, of course. Yeah.
Okay, so what I proved right now is that if you look at this Hilbert space, we had then all states are of the form, the action of some operator in this boundary algebra, which consists of all polynomials in 0 to epsilon acting on the vacuum. Okay, this result I just proved, it might be surprising, but actually it's not a very strong result. In fact, you would have noticed that in proving this result, I didn't even use gravity anywhere. So in fact, such a result holds even in the absence of gravity. So now I want to prove a more interesting result, which is much stronger, which is that any two distinct states can be distinguished by an element of A boundary. This is very different from saying that they can be created by an element of A boundary. Okay, to say that they can be distinguished is different from saying that they can be created. Okay, so how do we prove this result, which is what we want to get at? So we'll again prove it by contradiction. Say that we have two states which are unequal. If the states are unequal, then by definition, that means that there must be some operator to which these two states endow different expectation values. And what I want to show is that this operator must belong to the boundary algebra. So let me take this operator and let me expand it in some arbitrarily chosen basis. That's the expansion, the sum of CNM NM. Now by the previous result I proved, you can write the state ket n as the action of some element of the boundary algebra on the vacuum. And you can write the state bra m as the action of some other element of the boundary algebra on the vacuum. And that leads to the second part of the equality in the first equation. But notice that this projector on the vacuum omega omega that is in the middle is just p omega, which by our second assumption that we made some time back belongs to the boundary algebra. So this is the thing where we crucially use gravity. We use the fact that in a theory of gravity, which is not true in any other theory, in a theory of gravity, the projector on the vacuum belongs to the boundary algebra, in that you can use the boundary algebra to project onto a unique state. Because this is the case, notice that you can write this operator x now as just C of nm into xn into p omega into xm dagger. And every expression, every element in this expression belongs to the boundary algebra. Since it's an algebra, it's closed under products and linear combinations. And therefore, this x must belong to the boundary algebra. So using these two results, the fact that you can create any state by acting with an element of the boundary algebra, and the fact that you can project onto a unique state in the presence of gravity, we've been able to show that any two states that in the theory are distinguishable by operators in this boundary algebra. Okay. So this, let me just recap what we assumed and what I think we showed. So we assumed that first, that the vacuum remains unique in global anti-de Sitter space, which was again a semi-classical observation coupled with an assumption about the UV theory. Second, that the vacuum can be identified through a boundary Hamiltonian. Once again, a semi-classical assumption and then extrapolated to the UV theory. Third, that we can restrict to states produced by exciting this vacuum from the boundary at all times, which I argued was a good assumption because this was closed and this was a good superselection sector. And then subject to these three assumptions, we showed that all information about the bulk state can be obtained from an infinitesimal time interval on the asymptotic boundary. Okay. So that's, let me say a few things and then maybe I can stop for questions. Let me anticipate a few questions. First, this trick of course cannot work without gravity. If I tried to make a statement of this kind in the absence of gravity, it would be false. Even for gauge theories, for instance, if you had a gauge theory, non-gravitational gauge theory contains exactly local gauge invariant bulk operators which just commute with all elements of the boundary algebra. And so in particular, if you think of the two states that are on the screen, the state psi and another state formed by acting with a unitary e to the I trace of f squared localized at the point 0, whereby the point 0, I mean the point in the center of ADS, you see that the state psi and the state psi acted on with this unitary cannot be distinguished by any conceivable boundary measurement in a non-gravitational gauge theory. And so non-gravitational gauge theories are not holographic, which is of course good. That's a basic sanity check that we've done. Second, this trick cannot work without quantum mechanics. In the classical theory, as we all know very well, in GR 101, we are completely free to specify initial data in the interior of a ball independent of data outside the ball. So, if I just give you data in a ball, all I can tell from outside the ball is the total mass. I can't tell you what the distribution of the mass is. So if you think of the red dot, the two pictures on your screen, and the blue dot, which is the same mass now distributed over a larger interval, these are clearly distinct states in the classical theory, but they're indistinguishable from the brown region in the classical theory. And the reason for that, one quick way to see why that is the case, is that in the classical theory, you can only measure the expectation value of the Hamiltonian, which gives you, which tells you something about the state, but only the expectation value. But in quantum mechanics, you also have access to the moments of the Hamiltonian. And there is no notion of the moments of the Hamiltonian in the classical theory. The classical theory, expectation of h to the m is expectation of h the whole to the m. And therefore, in quantum mechanics, you get more information about the bulk state than you would in the classical theory. And that's another sanity check. Clearly, classical gravity also cannot be holographic in the sense I discussed. Okay, one last thing. Yes.
This is Aaron Wall here.
Yes.
The hidden under Rifa Khan. Can you comment on the relationship of this to Don Merrill's argument? He had a very similar argument for boundary.
Yeah, it's a similar argument. I referred to it in the beginning. So that's right. So indeed, there's a similar argument. There's some detailed differences in what we did. In particular, there's this, I've tried to make assumptions not about H being the full Hamiltonian, but only about projecting onto low energy physics. And then I tried to be more precise about the precise Hilbert space that we are restricting to. But certainly a lot of this is connected to what Marolf did.
Right, well, I had a question about your assumption. I guess the big difference from what Marolf was doing is it seems you're trying to weaken this assumption that the Hamiltonian is necessarily the same as the gravitational energy.
Yes.
I'm not totally sure why one would weaken that assumption, but if you did, isn't it still a very strong assumption to say that they have the same ground state?
So I can't hear you very clearly. Could you please repeat the question? You're right, I'm weakening the assumption, but I couldn't hear what you said after that.
Can you hear me well now?
Yeah, please go on.
Okay, so, if I have some operator, some energy operator,
Yes.
call it H, and then I decide my gravitational energy is that plus some perturbation that matters at high energy.
Yes.
And usually in quantum mechanics, you would expect that if you perturb the Hamiltonian in some random way, that even if it's something that only matters normally at very high energy scales, you might expect it to shift the energy levels down at the bottom a little bit. That is, it's quite important to you that the two vacuum states aren't just approximately close to each other, but they exactly coincide. And I'm not sure why one would assume that. But
Yeah, I think if you said that the vacuum projector was not correct, but was accurate to an order 1 over n, then I think you would have to insert 1 over n's here. So you would have, so if you went back to this formula, you'd have to insert 1 over n's here. But if you have two states which can be distinguished to order 1, this formula will still work in the presence of 1 over n's. But you're right, you could try and add 1 over n's to these. So well, I guess what you're saying is that the projector by the semi-classical operator may not be the projector onto the true vacuum, but the projector onto true vacuum up to some correction. And you could add corrections to this formula.
You're saying that with the error terms, this argument is formally still valid.
I think it would still be valid, yes.
All right, thank you.
Yeah. Just one more difference with the Marolf argument is that Marolf didn't write down a formula of this kind. His argument in detail was that you could take an operator one time and evolve it using the Hamiltonian. And for that, you really need the Hamiltonian of the semi-classical theory, the gravitational Hamiltonian, to coincide with the Hamiltonian of the full theory. So that the reason to write down a formula of this kind is to weaken that assumption. But we can discuss more.
Suvrat?
Also, in Marolf's paper, he says that he expects the same argument to apply purely in the classical case, whereas you seem to be saying it's not true in the classical limit.
I don't think he says that, but it can't be true in the classical limit clearly, because you can, you take a spherically symmetric distribution of matter and, take a compact distribution and a spread out distribution, and from outside, they look exactly the same in the classical theory.
The argument had to do with evolving with the classical Hamiltonian using the Poisson brackets, and there is this Liouvillean operator, and if the Hamiltonian was a boundary term, you could still do.
Well, but I mean, don't we have a clear counterexample in that let's just take like the Schwarzschild solution, and let's take the Earth and something which is 10 times more compact than the Earth, and you just live outside, and you will never know the difference between them unless you go inside and probe.
The classical limit, in the classical theory, it's very natural to have algebras that are not closed under the Poisson flow. Whereas in quantum mechanics, the analog of the Poisson flow is just exponentiation.
But the Poisson flow is exponentiation, right? In some.
Yeah, I think Ted Jacobson discusses this in one of his papers, this issue about the analyticity. So, I mean, we could discuss a little bit more about this, but I mean, in the classical theory, it's clear that we do have this counterexample. But you're right. I mean, the issue that Adam is bringing up is also discussed by Jacobson and collaborators in one of his recent papers. On, I think it's called Information Paradox and Diffeomorphism Invariance, if I'm getting it right.
Yeah, just a small comment. We had this discussion in Santa Barbara with Ted, and there was some confusion about that analyticity argument, but maybe we can discuss that at the end.
Yeah, but I mean, we don't need to, we just look at the counterexample you get by the Schwarzschild solutions with different densities of matter inside. And it's clear that from outside, you can't distinguish them. And that's because you only get to measure the expectation value of the Hamiltonian. But we can discuss more.
Okay.
Yeah.
Suvrat, before you go on, we have one more question from Emil. Emil, you can speak up?
Sorry, I had to unmute myself. Yeah, I'm just confused about the free lunch that you seem to be getting. So, in holographic context, sort of the number of low energy observables is tiny. And yet, the number of observables in the full theory is order n squared. And so it seems like you're getting way too much information about what you can make with n squared, gluonic operators versus what you can, measure by taking combinations of single trace operators.
Yeah,
could you comment?
So, maybe the next thing I'm going to say might help to clear that. But we could do two things. We could think about low energy states, which you can get by acting with small elements of this algebra on the vacuum. So you act with simple elements, a few single trace operators in the vacuum. And then you would be able to distinguish them by using similarly simple observations on the boundary. Or then you could talk about, how hard is it to distinguish black hole microstates. Now, for that, this argument would formally go through, but then it's very important for it to formally go through that I'm considering the full algebra of operators. So if you think about it that way, that's not very surprising. That's the statement that, you take the algebra of all glue ball operators and, you produce also the gluonic operators. But as I want to emphasize, this is a statement that also has content at low energies when you have a small set of states and a small set of operators to play with. But the objection you mentioned, which is that it's true there are many more operators in the theory, but it's not so surprising that you would get them by taking the algebra, by taking all possible polynomials of the low energy operators.
So if I have two black hole states,
Yes.
and I'm sitting way, a parsec away,
Yeah.
what am I supposed to do to measure which microstate I have?
Well, you have to measure this operator. I mean, first, so let's say you knew which microstates both were in, and you knew which operator would distinguish it for you. Then you would have to measure. You'd have to measure this very complicated operator. So in the case where you had black hole microstates, these operators xn and xm would be extremely complicated. They would have of the order of n squared insertions in single trace operators. So you would then have this operator, which again has order n squared insertions. It's some polynomial of order n squared. And the statement is you measure this very complicated polynomial, which has these n squares and has this p of omega sitting in the middle. And then you distinguish which microstate you're in. But it would be a very complicated polynomial.
So if I have to stick in those n squared operators, won't they make another black hole or bigger black hole? How can I do this non-destructively?
Well, this is a statement about measuring expectation values in a given state. Now, there's another statement you could ask, which is how do you physically measure those expectation values? So right now I'm assuming mathematically that you have a state and you're allowed to measure expectation values of any element of the algebra. But then maybe the question you're asking is how do I physically go about measuring elements of the algebra? Is that?
Yeah, I mean, I have a small, you're only permitting me a small time band.
Right.
And it seems like if I put some local operators near the boundary and I have to put n squared of them in there, I'm going to create some gravitational shock wave that goes in and makes something enormously energetic.
Yeah, but this is a question that goes beyond the algebraic formulation of the theory. You know, the statement I want to prove right now is a mathematical statement, which is by measuring an element of the algebra, I can distinguish between these two microstates. And this is something that's unique in gravity and wouldn't be true in other theories. The question you're asking is, there are elements of the algebra that look like they're very complicated to measure, that are very hard to measure. So I don't have something very sharp to say because this is a question that's that's then a question of how do you make measurements of trying to come up with a full measurement theory in a theory of quantum gravity. How do you turn on sources so as to measure this very complicated operator? But at the algebraic level, the question is mathematically well defined in that you have an algebra of operators and you're allowed to measure the expectation value of any element of this algebra. So that's the attitude I'm taking.
Okay, thanks.
Yeah. Okay. So let me say a little bit.
Can I ask a follow-up question? So
yes,
can you say this boundary algebra that you have, is it supposed to be any different than the full CFT algebra?
Yeah, in ADS-CFT, it would become the full CFT algebra. There are two differences though. First, because my algebra lives on a small time band. The CFT algebra, of course, lives on a time slice. It lives at t equal to 0. The t equal to 0 to epsilon is completely redundant in the CFT. And in ADS-CFT, this would become the CFT algebra. But I didn't want to assume ADS-CFT. I wanted to say, look, here we have this algebra of some bulk observables, and then we multiply it and we come up with polynomials. And we don't know about ADS-CFT. So, let's say we go back to many years ago when we didn't know about ADS-CFT. The question is, does this algebra you get by taking these bulk operators near the boundary and multiplying them, does it contain all information about the interior or not? And what I'm trying to argue is that it does. But you're right, from ADS-CFT, this algebra is also by the extrapolate dictionary, the full CFT algebra. And so this result is kind of obvious if you assume ADS-CFT.
I see, thanks.
Okay, so there are many questions about this, but let me just make one more statement. This might seem like an abstract argument, but in fact, you can verify this in perturbation theory. So you could consider the following challenge. Let's take the vacuum, and let's say we have some bulk scalar field, and let's act with a unitary operator that is some smeared version of this bulk scalar field on the vacuum. And this gives you some state, which is labeled by the smearing function f. And then the challenge is, can you back calculate what this function f is by making observations near the boundary? Of course, again, local QFT, it would be impossible, but in gravity, it's possible and not very hard. And what you do is you need to measure a 2-point function of the metric and an insertion of the same scalar field in the state psi. And you can check with a little bit of algebra that if you know this 2-point function for a small range of t in 0 to epsilon, you can back calculate the function f of r. So this is a statement about how you can get a concrete statement in perturbation theory for how you can get information about a bulk excitation using simple 2-point functions on the boundary. Of course, as we discussed, if you looked at more and more complicated states, I would have to look at more and more complicated correlation functions to distinguish them. Okay, let me say one thing about black holes though. Let's say in one case at least you can get some information about black holes. So let's say we assume that we have a black hole which has a very narrow spread in energy. So it has a small spread in energies, and this we assume that, and then we consider another state that is the same almost energy eigenstate acted on with another excitation of the kind that I mentioned previously, where you take a scalar field and you smear it over some region and then you act with it on this energy eigenstate. So you could think of this as creating some kind of shell behind the horizon. You can determine what the profile of this shell is again by measuring this kind of a 2-point function. It's slightly more complicated. You have to subtract off some expectation value, but you can check once again that you can determine what the profile of this function f of r is. So if I gave you this class of microstates, which is a very special class of microstates, it's almost energy eigenstates excited in a particular way with a scalar field, then you can detect what that excitation is from outside, again by measuring 2-point functions. Okay, so now I spent a lot of time on ADS, but now I'm going to go on to flat space, and I think I can go faster because I hopefully emphasize most of the technical details. Are there any other questions? I know we had a lot of questions. If there's some other questions, I could take them now and then go on to flat space. Okay, so then I'll continue. So now I would like to understand how quantum information is stored in quantum gravity in asymptotically flat spacetimes, and a lot of work has been done in this, some of which was discussed already by Malolf and others, and of course, starting work by De Boer and Solodukin, and by Strominger and Bakchi and Grumiller and many other people. So I'm going to try and describe how these results generalize. Let me describe some intricacies first of all, some things that are different about flat space. Some things, one of the things that's obviously different is that just to emphasize, I'm going to consider 4-dimensional spacetimes, asymptotically flat spacetimes. And something that we've learned through a lot of research in the past few years is that the vacuum is infinitely degenerate in 4 dimensions. And then the other complication that we have in flat spacetime is that null infinity only has information about massless particles, which is not quite the same as ADS. And then there's a third issue, which I'll describe what the relevance of that is, which is that the standard way of taking the boundary limit in flat space, this way that was developed by Ashtekar and collaborators in asymptotic quantization, actually drops all interactions. So the theory on null infinity really becomes a free theory, which is different again from ADS. But nevertheless, I'm going to try and persuade you that this technique that I described in some detail generalizes nicely to 4-dimensional asymptotically flat spacetimes, and provided we consider massless excitations, it yields some interesting results. Okay, so let me just describe the setup. I'm going to consider the standard boundary conditions for 4-dimensional asymptotically flat spacetimes. So I have a spacetime which is just Minkowski space to leading order, and then there are fall-offs. Just for some notation, this CAB is sometimes called the shear, and I'm going to consider future null infinity, and everything I say will have an analog for past null infinity. If you look at the derivative in retarded time of this CAB, that's sometimes called that is called the Bondi news. And then I might have other matter fields. For instance, I might have a massless scalar field, and I'll impose the standard 1/r fall-offs for such fields as well. Okay, now just some more review. So in asymptotically flat space, something interesting happens, which I think was noticed first by Ashtekar now 40 years ago almost. And it's the fact that the full nonlinear theory of gravity trivializes on Scri+. In particular, you can compute some exact commutation relations between, for instance, the Bondi news and the shear. And these relations are not computed in the limit where G Newton goes to 0. They're just exact relations that hold in the full nonlinear theory of gravity. And then there are some exact constraints that relate the evolution of the Bondi mass to a quadratic to the matter stress tensor and the square of this news. And these are results which hold in the full nonlinear theory. Okay, then there's something else, some more review. The theory in 4 dimensions has an infinite number of what are called super translation charges. These super translation charges can be rewritten into what are called soft and hard charges. And these soft charges label the different vacua of the theory, and then the hard charges tell you the super translation charges of various excitations on top of these vacua. So in particular, as I said, we have a large number of vacua. These vacua are labeled by their soft charges. And then on top of each vacuum, you can again build up a Fock space. The standard way to build up a Fock space is to just think of the kinds of excitations we have in constructing an S matrix. You take some function on null infinity, you smear the news operator or one of the matter operators with this function, you act with it on one of these soft vacua, and you get some excited state. And the full Hilbert space of massless particles can be written as the direct sum of all of these states that are built on top of these different soft vacua. So this is what I will call the space of massless particles, and every statement I make will be confined to this Hilbert space. And this space excludes massive particles for now. Okay, now I need to define the analog of what I call the boundary algebra in ADS. So I'm going to define once again an algebra of operators that lives in some interval at null infinity. So my algebra once again is going to consist of these subleading fall-offs, which as I said were the shear and maybe the subleading fall-offs of the matter field, and also the Bondi mass. And then I'm going to take polynomials in these operators. Okay? And this is what I'll call the algebra AU, which lives at some point U. And then I also have the algebra that lives near the past boundary of future null infinity, and that I'll call A minus infinity. So I don't know how clear the pictures are on your screen, but the red strip, the small red strip near one of the edges of the diamond is where A minus infinity lives. And then the blue strip somewhere in the middle of Scri plus is where this algebra AU lives. So once again, I'm thinking of the algebra of all of these bulk operators pushed to the boundary and then smeared over a small amount of retarded time. Okay, so far I assumed what was already known, and I made some definitions. I reviewed some of the semi-classical results. Now I'm going to assume, as I did in the case of ADS, that some aspects of the semi-classical theory carry over to the full UV theory of quantum gravity. And this will lead to more interesting results because unlike ADS, we do not have knowledge of ADS CFT. So this will lead to some interesting statements about how quantum information is localized in asymptotically flat spacetimes. And I'm going to make various kinds of assumptions. And I'll point out that by making some very weak assumptions, we already obtain interesting results about how quantum information is stored in asymptotically flat spacetimes. And by making stronger assumptions, we can then obtain stronger results. So the first result I'd like to establish, and I'll tell you the assumptions that go into that, is that any two distinct states in the space of massless particles can be distinguished just by observables near the past boundary of future null infinity, this algebra that I call A minus infinity. So this is my first result. And I have to tell you what the assumptions are. So I need the following assumptions. I need the assumption that in the full theory of quantum gravity, the vacua are identifiable by operators near the past boundary of future null infinity. This is manifestly true in the semi-classical theory because all vacua are labeled by super translation charges. But in particular, I'm willing to allow for the possibility that there are additional charges in the full theory, provided these additional charges are also defined near the past boundary of future null infinity. The second assumption I need is that the operators that map the space of vacua back to itself are also contained in this algebra that lives near the past boundary of future null infinity. Once again, in the semi-classical theory, this assumption is manifestly true. It can be checked explicitly, and it's an assumption about low energy physics. And so one might reasonably expect it to remain true in the full theory. But in any case, I need to assume this.
Suvrat, can I ask a question?
Yes, please.
So it's a question about your assumption 1.
Yes.
I don't think you can identify what vacuum you're sitting in using only the super translation charges, because the super translation charges are abelian.
Oh,
What you can determine, yeah. Yeah, you can't distinguish exactly which vacuum is in. You can distinguish if the vacuum has changed.
Yeah, thank you. I'm not going to use the super, so maybe I should say it differently. Vacuum and the full theory are labeled only by eigenvalues of operators near I plus minus. That's different from being able to distinguish them. So you're absolutely right that if I just measured super translation charges, I wouldn't be able to distinguish operators. But what I meant to say here is that vacuum and the full theory are labeled only by eigenvalues of operators near the past boundary of future null infinity, which is true in the semi-classical theory. Because they're labeled only by super translations, even though, I mean, and I'll discuss how you need to identify them.
Okay.
Yeah, so that's a more precise statement. Okay. So now let me just describe how this, I'll run through this argument fast. So of course, using the positivity of the full Hamiltonian, once again, you can write any state in this full Hilbert space of massless particles as an action of an element of this boundary algebra on one of these soft vacua. And this argument works exactly the same way as in ADS, and it uses positivity of the full Hamiltonian and analyticity properties, and tells you can create all states just by acting with operators in a small time band on a vacuum. Okay. Second, by this assumption I just made, these projectors onto the vacua, and also operators that cause transitions from one vacua to the other vacua live in this boundary algebra. So as Prahat just pointed out, if you just looked at the super translation charges, you'd get projectors, but you also need these operators that don't commute with super translations, that give you transitions from one vacuum to the other vacuum. The shear, for instance, gives you one such set of operators. And by these two assumptions, the fact that you can first project onto individual vacua and also cause transitions, both of which were assumptions I made, these operators T, SS prime live in the boundary algebra. And now any operator that maps the space of massless particles back to the space of massless particles can once again be expanded in terms of this Fock space that's constructed on the different vacua. And by the same argument I made in ADS, this operator can now be pulled back to an operator that lives in the boundary algebra. So in this expression, you see these states N and S and M and S prime are states built on the Fock space on top of the vacuum S and the vacuum S prime. Now you can create these states by acting with some element of the boundary algebra on the vacuum S and the vacuum S prime. And then you take the S prime, the ket S, bra S prime operator in the middle, and you call that TSS prime. And the assumption I made previously, which is true in the semi-classical theory, is that this operator also belongs to the boundary algebra. And so once again, this full operator A belongs to the boundary algebra. And therefore, any operator that that maps the space of massless particles back to itself lives in this boundary algebra. And that tells you that all information about the space of massless particles can be obtained by looking at operators near the past boundary of future null infinity. Okay, now I want to make a stronger statement, which will rely on a stronger assumption, and this actually will bring me closer, in a sense, to the arguments that Marolf made. So the second statement I'd like to make is that any information that's accessible at some point on future null infinity, at some point on Scri plus, which I call U1, is also available on any cut to the past of that point. So if you look at your screen, you see these cuts near U1 and U2. What I would like to claim is that any information that's accessible at U1 is also accessible at U2. Okay. How does that work? Well, so in the semi-classical theory, as I pointed out, there are some exact commutation relations one can derive. And those commutation relations tell you that if you look at the Bondi mass at some cut, that Bondi mass acts like the Hamiltonian for all operators to the future, but not like the Hamiltonian for all operators to the past. Now, what I would like to assume is that this commutator gets corrected only by local terms. So, you could even say that I'd like to assume that this commutator is unchanged in the full theory. So you might have thought this is a crazy assumption because, you derive some assumptions using the semi-classical theory. And, why would you assume that they don't get corrected in the UV theory? But in fact, this is not such an unreasonable assumption because these commutators depend only on quadratic terms in the effective action. And that's because of this funny property that I mentioned, which is that interactions tend to drop off as you go towards null infinity. And therefore, it's not so unreasonable to assume that these commutators that you derive in the asymptotic quantization program actually hold in the full theory of quantum gravity. If so, Then, because as I said, this M of u acts as a Hamiltonian for operators at larger values of u, I can always take the operator at some value of u and I can evolve it forward and backward using this Bondi mass. Sorry, I can evolve it forward in time using this Bondi mass. I can't evolve it back in time because this M of u doesn't act like the Hamiltonian for operators that are to the past. But it is the case that if I give you information near this red cut, then using the Bondi mass as a Hamiltonian, I can get all information about all operators near the blue cut. But I can't do things the other way around. So this is a somewhat more intricate structure in ADS because we seem to lose information as you move away from the past boundary of future null infinity. So the first result I established, which was based on very weak assumptions, was that all information is available near the past boundary of future null infinity. And then using stronger assumptions, I'm now trying to argue for this nested structure of information. That information that's available at a cut is also available at all past cuts, but you lose information as you move to the future. Okay, so this is a summary of the results I established, and I went through them fast because technically they're very similar to the ADS results and the assumptions I made. First, I assumed that if you assume that vacua are identifiable by charges inscribed at the past boundary, as Prahar correctly pointed out, I should have said the vacua are labeled only by charges at the past boundary. And if you assume that operators near the past boundary of future null infinity can map one vacuum to any other vacuum, that already, those weak assumptions about the low energy structure are sufficient to tell you that all information about massless particles is available near a scribe plus minus. If you make a stronger assumption, which is that the commutators and constraints from asymptotic quantization are exact, then this tells you that information at any cut of scribe plus is available in any earlier cut. And of course, the first result is a subset of the second result, because you can see if you just take the second result and push it all the way back to minus infinity, it'll tell you that all information about scribe plus is available at its past boundary. Okay, so these are the results I wanted to establish for flat space, and I went through them fast because they're very similar to the ADS results. Are there any questions? If not, I'll spend some time, maybe 10. Can I have 10 minutes more, Ignacio?
Yes, sure.
Okay, so maybe I can spend last 10 minutes on the information paradox. But if there are any questions, I can take them here.
Sorry, just a question. Hi. How does the memory effects fits into your description? Suppose I have a shock wave at a certain u star between minus infinity and plus infinity.
Yes.
Can you keep track of that near
Yes.
scribe plus minus?
Yes, actually you would need the same kind of correlator that you had previously. So in our paper, we have an explicit calculation of this. I'm just going to go back a few slides and I'll tell you how it's this perturbative correlator. That shock wave actually is a particularly simple thing to identify. You need to measure this kind of a correlation function. So let's say your shock wave was produced by taking the news operator and smearing it, say around u equal to 0. So you take a vacuum and then you create a shock wave by taking the news operator and smearing it around u equal to 0. And you want to measure it near u equal to minus infinity. The expression on this slide is an expression in ADS, but it's the same kind of 2-point function that you need to measure, and you can actually detect in the quantum theory the presence of that shock wave near the past boundary of future null infinity.
Okay, thanks.
Suvrat, excuse me, I have a rather technical sounding question, but I've often heard that when you do these multiple vacua, you actually get a non-separable Hilbert space. And a lot of the results you proved in the ADS-CFT case were, I think, at least their usual description depends on a standard separable Hilbert space. Do you have any comment about that?
Sorry, no, I do not have something very intelligent to say about that. I'm maybe mathematically more naive, but I would have, yes, so I don't have something very intelligent to say about that. I would have thought that we could try and bin vacua up by taking spectral projectors onto some range of soft charges, and then try and try and get some. I mean that's how I would always do things, in that I would try and come up with some way of regularizing the space, and then work within that regularized space.
I see. Okay. Thank you.
Maybe there's something more mathematically sophisticated to be said about that, but I don't have anything more to say about that.
Suvrat, one more question. Is there any comment you can make about infrared divergences in this structure? So of course, in the full quantum gravity, Yeah. So yeah, it's a somewhat vague question. So it's okay if there's no good answer.
You mean
What's the
dynamic?
Yeah.
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 Actually,
Like if I have any radiation coming in, at least semi-classically, that gives rise to infrared divergences. And how does that impact
yeah, of
the
course.
structure?
I'm working within this set of states, which is in which you think the S matrix is IR finite, which are these states which are eigenstates of the soft vacuum and then excited with News operators. So these are states in which you expect the S matrix to be IR finite. They're like the analog of Adiev-Coolidge states. They're not quite that, but I'm starting with eigenstates of super translations and then exciting them with only the News. But that being said, there's a broader question. I think one of the things, as I pointed out here, was that because you kind of drop interactions as you go to null infinity. This is a statement about how quantum information is localized on null infinity, but it doesn't somehow have something so interesting to say about dynamics. And that's kind of one thing which is different about flat space compared to ADS. And that in ADS, by looking at the dynamics near null infinity, you're able to reconstruct also dynamics at time like infinity. You're able to reconstruct some dynamics about the bulk. But in null infinity, the theory really trivializes. So it's hard just from these considerations to say something about dynamics. Another way to say that is that dynamics is a question of how states at scribe plus map to states at scribe minus. My statements here are solely confined to scribe plus, and I would have analogous statements for scribe minus, but they would not say anything about the map between the two Hilbert spaces.
Very good. Okay. Thank you.
So let me spend about 10 minutes on the information paradox. So of course there is we have a question that's often asked about the information paradox is you have a star and the star collapses to a black hole and evaporates to form Hawking radiation. And the kind of question we often tend to ask is how does information come out of the black hole as it evaporates? And this is of course a natural question to ask based on everyday physical intuition, which is, if you have a piece of coal, it evaporates. You ask, how does the information come out of the piece of coal as you collect the radiation? But the results I described previously suggest in a quantitative sense, as I'll describe now, that the information is always outside. So this is perhaps not the right question to ask in gravity. What do I mean by that? You see, there's a precise way of quantifying how the information comes out. And the way of doing that is to try and define a state at null infinity. So this was an analysis that Page did now almost 30 years ago. And Page pointed out or argued that, if you looked at the state that's marked by the thick red line on scribe plus, which is some section of null infinity, and you looked at the entropy or the von Neumann entropy of that state as you moved u from minus infinity up to plus infinity, then that von Neumann entropy would obey the Page curve. In that, in the beginning, you would have no information, and then slowly, you'd have Hawking radiation, and so the von Neumann entropy would look thermal, and then the entanglement in the Hawking radiation would cause the von Neumann entropy to go back again. So if you started with a pure state, at the end, you would end up with a zero von Neumann entropy. But if you believe the results that I described previously, then they tell you something quite different about the von Neumann entropy. In particular, they tell you that if you look at the von Neumann entropy of the state defined on minus infinity to some u0, that's independent of u0. And the reason for that is that I argued that all the information on some segment of scribe plus was already available in a small interval near the pass boundary of scribe plus. And therefore, by extending this segment higher and higher or further and further along scribe plus, in a theory of quantum gravity, you don't really get any more information. If you also accept the second result I mentioned, then it tells you that you take any segment, whether or not it includes minus infinity, the von Neumann entropy of that segment is independent of its upper bound. That you can extend the segment further and further towards, further and further towards larger values of u, and the von Neumann entropy would not change. And that's again based on the fact that I stated that information that's available at any cut of scribe plus is also available at a previous cut of scribe plus. So if you believe this, just to put this in the frame of the previous picture I had, as I said, the fact that information about massless excitations is available near the pass boundary of future null infinity tells you that the von Neumann entropy of a segment minus infinity to u is independent of u, and similarly about the second result I had. So if you believe this, then it tells you the page curve should look like this for this segment U. In that, as you you define a state on future null infinity, you have this segment that extends from -infinity to U. You extend it towards more and more U, larger and larger U, and you don't get any information. Now, this is not so surprising because, you know, the page curve is, if you look at the way Page derived it, it was based on an assumption about the factorization of the Hilbert space. And we know that that assumption fails. And in fact, the point of the results I've been trying to show have been about the importance of the fact that this assumption about factorization of the Hilbert space fails. The reason I have a finite intercept in this diagram is because I ignored discussions of massive particles. Okay, let me say a little bit about this, and I'll come back to more recent results on the page curve. But let me say a little bit about what the analog of this result in ADS-CFT is. This is just a statement that if you think of a small black hole that forms and evaporates in ADS-CFT, and you think of the full algebra of operators near the boundary, then the von Neumann entropy of that algebra is just always zero. The state is just always pure. So if you think of this process on the left part of the figure and think of this red, purple, and green lines, at all points, the von Neumann entropy is just zero. So the state is always pure, and near the boundary, you always know that the state is pure. You might say, well, you know, wait a second, maybe it's the case that the state is always pure, but maybe once the black hole has evaporated, as it has in these blue dots, it's easier to get the information than it was before the black hole had evaporated. Okay? And that might be a natural assumption. You might have thought that at this time t2, which is an intermediate time, it's somehow very hard to get information, but at time t3, it's much easier to get information because you can collect the Hawking radiation. I don't have something very precise to say, but let me just say that if you make a crude estimate, this is not the case. And the reason is the following. Before the black hole forms, when you just have matter outside at this time t1, it's indeed the case that information is easy because you can just look at some simple operators maybe and get information about the distribution of matter. After the black hole forms at t2, as we discussed in the middle of this talk, it's pretty hard to detect which microstate the black hole is in, and that requires n² point correlation function. So in particular, requires S point correlators. But after the black hole evaporates, which is this time t3 that I have marked, information is still hard to recover. If you want to use the Hawking radiation to recover the information about the original state of the black hole, that also requires n² point correlators. And so it's not clear that there is any hierarchy of difficulty in getting information between when the black hole exists and when the black hole is completely evaporated. This is not a watertight argument, it's just an estimate, but I wanted to point out this estimate. Okay, so if you believe these arguments, then of course, as I said, there are several aspects of the information paradox that you could resolve. These are now, I guess, familiar to most people here, but let me just go through them quickly. For instance, there is the famous cloning paradox, which tells you that, you know, if you have a black hole which is formed from collapse, you can draw these nice slices and you can argue the information is both outside and inside. But that's not a paradox from this way of looking at things, because you should just think of this information outside and inside as being information that lives at two different parts of future null infinity. And we already argued that information at any future cut was already available at a past cut. And that's not a feature of cloning. That's just the way quantum information is stored in gravity. The same is true if you think of the strong subadditivity paradox, which once again, there was this, the paradox relies on the assumption about monogamy of entanglement. It tells you if you look at the near horizon region, you can argue it's entangled with the region far away and also the region behind the horizon. Once again, you can translate this to statements about information in different parts of future null infinity. And if we agree that information at a cut is also available at the previous cut, then there's no violation of monogamy of entanglement. It's just the fact that this information is stored redundantly in this manner in null infinity. Okay, let me say a little bit about the page curve, and then I'll conclude. I've tried to argue that the von Neumann entropy of the black hole radiation is not described by the page curve, and in fact, I think this is the reason that gravity is interesting, precisely because the information is always outside. But I'd like to emphasize that it's possible to change the question appropriately so that the answer becomes the page curve. And I also want to make contact with some recent literature on the page curve. So in particular, the simplest conceptually, although not technically, way to get the page curve is to think of what's called the plasma ball solution. The plasma ball solution is a solution which you should think of as a lump of the quark gluon plasma, that's surrounded by some region of the confined phase. Now, the important thing here is that in this setup, the Hilbert space factorizes because we look at this setup on the boundary. And on the boundary, we do know that the Hilbert space factorizes. And if you look at how this lump of the quark-gluon plasma, which corresponds to a localized black hole in the bulk, decays, how the matter and energy in this region D spreads out into the region C, then you do expect to see a page curve. And the reason, once again, I emphasize is because you have a setup in which the Hilbert space does factorize. And that setup is given to you by thinking about the boundary and thinking about these regions D and C on the boundary, not some regions in the bulk. Okay. The same way you could think of, as has been done in a lot of the recent literature, you could think of a black hole in ADS and you could couple it to a bath. And then you could look at how the initial state decays into the bath. And of course, on the boundary now, you do have a factorization, which is a factorization of the CFT that describes the ADS black hole, and the bath that describes an auxiliary system. And you compute the entropy of the bath, and you do expect to see a page curve because that's an ordinary non-gravitational setup where a CFT is transmitting energy into a bath. I mean, this is a question of terminology. I would say that the bath is not quite the radiation, because the bath captures regions inside the black hole, and that was, of course, the point of the island prescription, but it also misses some regions outside the black hole, which also capture the radiation. So I would say, I would not use the terminology radiation for the bath, but of course, it's true that the curve of the bath obeys the page curve. Okay. There's a similar, of course, more detailed analysis one could do where you take a black hole and you couple it to CFTs. And then once again, if you look at the red strip on the figure, then the entropy of these red strips is believed to obey the semi-page curve on the right. But it's very important, I think, in this picture that this relies on gravity being non-dynamical in part of the space, in that there is a point where you have a black hole and then you switch off gravity at some other point. And I think that's what leads to this semi-page curve. In particular, if you looked at a real black hole and thought of a real Schwarzschild black hole in our world, then I claim that you would expect the trivial page curve because it's not true that gravity switches off at some point. It is, of course, true that gravity is weak on the red slices, but I think it's incorrect to suggest that because gravity is weak, the red slices should obey the same curve that they do in the setup where gravity is zero. And the reason for that is what I emphasized previously, that if you really want to see the page curve, you need to measure very high point correlators in the red slices. And these high point correlators are sensitive to gravitational effects. And so I think it's important that just because gravity is weak, one cannot, in our world, ignore the fact that these gravitational effects are important or make an analogy with a setup where gravity is switched off in the middle. So I think it's important that gravity, to recognize that gravity does localize quantum information unusually. And I think if one neglects this and says, well, you know, gravity is weak and so we'll ignore this fact, I think this repeatedly does lead to paradoxes, including some of the paradoxes that I described. Okay, so I think I'm done. Let me just conclude and then I can take more questions. As I said, the main point I wanted to emphasize in this talk was that in gravity, there's an unusual way in which quantum information is localized, which is that if you specify the wave function everywhere outside a bounded region, you're left with no freedom inside. And I think this is important even when gravity is weak. I tried to argue that this principle follows from semi-classical considerations. I tried to make my assumptions as precise as possible. In ADS, this is kind of an obvious statement. It just suggests that all information is available in asymptotic operators, which we already knew from the extrapolate dictionary in ADS CFT. In flat space, it leads to some interesting results. It tells you that information on scribe plus is available on its past boundary, and information on a cut of scribe plus is available on any past cut. And I think in the case of black holes, it tells you that asking the question of how the information comes out may not be the interesting question in gravity. And rather, the interesting thing is that the information never goes in. And if you really look at the fine-grained entropy, you would get a trivial page curve. Okay, so I'll just stop. This is a summary of the results, and sorry for going a little over time. Thank you.
Okay, Suvrat, so thank you very much for this very interesting talk. So I'm sure there's still questions online.
Yeah. Can I ask, Suvrat, so in the ADS case, we can couple this time-like boundary to a bath to get this page curve, this tent.
Yes.
You have a proposal in flat space. Let's say we accept this fact that if the gravity is active everywhere up to scribe plus, then we get this flat page curve. And then if we accept that, do you have a proposal for how to extract the radiation like into a bath?
Yeah, so we had some discussion of that. So I think, it may be that if you look at appropriate subalgebras, maybe you can get a page curve. But I mean, the one discussion we had was whether if you looked at the algebra of news operators and didn't include the Bondi mass, whether you would get something like the page curve. I think it's still not clear because of these issues with soft degrees of freedom and how much entanglement there is between hard and soft degrees of freedom. But I think maybe it is possible to think of a setup where you would get the page curve. But I guess one point I wanted to emphasize was that somehow in gravity, one interesting thing is that the information never goes in. So maybe rather than looking for the page curve, which maybe one can get in some way, one could ask questions of the kind that were asked previously, which is, how does one obtain information about a microstate? Like, what is the precise kind of correlation function you'd need to write down to obtain information about a microstate from outside?
Right,
So,
right. I agree. That's also an interesting question.
Yeah, say that there's a sense in which gravity is interesting in that the information never goes in, and that's the interesting aspect of gravity. And I don't want to rule out the fact that there's some way to get maybe there's a way in flat space where you have a clever enough construction which gives you the page curve by looking at a suitable subalgebra. It would not be the most natural construction of just the algebra on null infinity, but something more refined. But maybe that's possible.
Hi, Suvrat. Can I ask some question? This is Nori. So just to clarify what you said, you claiming that all of the information is always stored at the boundary in the presence of the gravity. Is that what you're claiming?
Yes.
And you say you define some algebra, boundary algebra,
yes,
which you consider whatever the bulk field, you just extrapolate into the boundary.
Yes.
And by collecting all of such a boundary operator, you can always distinguish what you have in the bulk. Is that what you're claiming?
Correct.
Including black hole microstates.
Correct.
So you should have order n square boundary operator.
Correct. For black hole microstates, yes.
But if you just consider low energy effective theory, you don't have such a order n square operator usually. Is that right? So you have to consider stringy state and so on and so on? Is that what
correct. So there are two statements I made. This formal statement I made about quantum information being localized near the boundary is already a contentful statement if you think of low energy states. So you could think of low energy.
Say again, sorry. Could you repeat?
I said it's a statement that already has content if you restrict oneself to the low energy Hilbert space. In that, let's say you think of states that are formed by the action of single trace operators on the vacuum. You already ask from the boundary, can you distinguish which single trace operator you acted with? So maybe I can go back to that slide on perturbation theory here. You see, you could already have done this kind of a trick. You could have said, let me take the vacuum and let me act in it with a simple operator. This is a simple unitary operator. And from the boundary, can you distinguish what was the function f of r you acted with? Already in a local quantum field theory or even in a gauge theory, it would be impossible to determine what this function f of r was. But by looking at simple correlators, you can determine, I claim in gravity, and this is a simple calculation, you can determine what this function is. Now you're right that if you start going to black hole microstates, then you have to look at very complicated correlation functions. So for black hole microstates, this is you might even say this is a formal argument. It's an argument that says that, if you look at the algebra of all of these operators, that will also allow you to distinguish different black hole microstates from one another. Yeah, it's hard to do computations in a precise way.
But I still do not get intuitively. I mean, after the Hawking radiation, we usually expect that after the page time, half of the Hawking radiation actually comes in, and the information begin to, come to the asymptotic region. But you are saying that always, even before the page time, you can extrapolate the information of the black hole microstate. Is that what you're saying? That's why page curve is totally different.
I think even after the Hawking radiation emerges, you still need to measure an S-point correlation function.
That's I agree. That's I agree, because of the order n square radiation you have to measure.
Exactly, but if you measure S-point correlation function even before the Hawking radiation has emerged, then this is already this very complicated operator that you just described. So you see, what I'm trying to argue is that if you are allowed to measure S-point correlators, then it's not clear that you have any more information after the black hole evaporates than before the black hole evaporates. You see, either you could say that we'll never measure S-point correlators. We'll just consider the non-gravitational limit where we have, we'll decide we can measure up to 100-point correlators. And then, of course, you would not see this effect that I mentioned, but you would also not see the page curve. Or you could decide we are going to allow the measurement of arbitrarily high point correlators, and then you would see the page curve. But you would also, you'd not see the page curve. Then you would be able to get the information out, but you would also get the information out before the black hole is evaporated. So, it's not clear to me that there is a regime of coarse graining. There may be, as Raghu asked previously, but it's not clear to me that there is some intermediate regime of coarse graining where you restrict to correlators of some complexity, which lets you see the page curve, but does not let you see the information before the black hole is evaporated.
Yeah, that's what we.
There may be, but it's not clear to me immediately that there is.
Okay, I'm not totally convinced, but yeah, I'll just shut up now.
Yeah.
Well, just one last comment. The existence of the horizon, right?
Yes.
That significantly gives a difference for the information. So it's quite hard for me, even before the page time, you have black hole horizon, and then just by correcting the same amount of the order n square correlated, you can extrapolate the microstate of the black hole. That's very
the horizon is a
counterintuitive.
But by the time you're measuring S-point quantum correlators.
That's quantum. That's a quantum. Right?
No, but you also not. It's not just by the time you're measuring S-point quantum correlators. So S is important. Then it's not clear to me that this retains any significance. Certainly from a classical point of view, the horizon is important, but that's a question of one-point functions. By the time you could ask this question actually in a more precise sense in ADS, which I tried to discuss here. Maybe I can. Right. Let's say we look at this picture, which is a picture of where you had some matter, it thermalized to form some quark-gluon plasma, and then it evaporated again, broke up into blue ball. Now you could ask, how hard is it to obtain the information at T2 and T3, which you can see? I think at both T2 and T3, you would still need to measure S-point correlators. It doesn't happen.
Yes, I agree.
Yeah, so this is the setup you mentioned, right? At T3, in some sense, the horizon is gone because the black hole has evaporated and you have only Hawking radiation. But from the boundary perspective, that it's very unreasonable to expect that the information will become easier, like somehow the system will unthermalize. So you will still need to measure very complicated correlators at both T3 and T2. So this is precisely the question you're asking. You see, from the bulk perspective, at T3, it looks like there's no horizon, and at T2, there is a horizon. But I think both times you need to measure like S-point correlators or n-squared point correlators.
So you're claiming that naive page curve, which goes up and then goes down, is wrong because of the long assumption of the factorization. Is that what you said? Is that right?
Yes.
And that is due to the more or less your assumption that the boundary Hamiltonian determines things. That's a crucial point. Is that right?
Actually, the precise statement I needed was that the vacuum could be identified. So there was some more
vacuum. Okay.
Yeah, it was a low energy statement, not that the boundary Hamiltonian is.
But that is also an important point, right? Boundary Hamiltonian.
Yeah, it was a boundary Hamiltonian, but I did not want to assume that the Hamiltonian of the full theory was a boundary term, but rather that the boundary term allowed you to determine the vacuum.
Okay, good. Okay, thank you.
Are there any more questions?
If no one has a question, maybe I can revisit the distinction between classical and quantum. So I posted in the chat and I checked Don's paper. He says explicitly.
I did not see the chat. I should see the chat. Sorry, please.
He just says that the statement with the e to the IHT is the same as the statement with e to the Liouville times time. So That's just so that's just one comment.
Okay.
But now let me come to your example, the example that you were saying about a star, and let's say we have two solutions that are different in the bulk.
Yes.
Okay. So I don't think it's well understood what the well-defined boundary or initial value data should be in ADS.
Yes.
But if there are two different solutions, there should be two different sets of initial or boundary data that lead to those two different solutions. Assuming classical gravity in ADS has a well-defined Cauchy data problem or boundary, whatever, initial plus boundary, whatever thing it is. So you can't say that, we can't say that we have two different solutions in the bulk, but they look exactly the same from the point of view of whatever initial data we were supposed to supply to get those solutions in the first place.
But sorry, but the initial, here I'm allowing you to measure boundary operators at a given instant of time, not for all times. So the question is, if in a small region like 0 to epsilon, if by measuring boundary operators in that region, if you can distinguish this red dot from this blue smeared out thing.
Yeah,
so,
but those things contain e to the I HTs, right? Where H is the classical or the quantum Hamiltonian.
But why don't we just specify initial data by having two different kinds of shock waves, or having just matter distributions of different densities, and you can evolve things, and you might have just got a static solution, but you might say that you evolve things and some information comes out later in some more realistic solutions. But certainly at a given instant of time, you don't know anything except for the total mass in the classical theory.
No. All I'm saying is the classical theory has some set of differential equations, right? That given some unique boundary data or initial data lead to unique evolution everywhere in the space-time.
I agree, but right now we are just talking about initial data. I mean, this is, in a sense, the question about information was always a question about, on a given time slice, if I give you information near the boundary, do you also have information about the bulk? So in the classical theory, it's almost clearly not the case, right? Because I could set up the initial data just on one time slice as either a very compact object or a very
what I'm asking is whether that initial data is of any significance from the classical theory point of view, because we know it's not going to lead to a well-defined, Einstein equation problem.
Oh, I didn't know. Why is that?
Well, just because we could have, in principle, we could have added the sources in the future, right?
I didn't understand. So let's say we just switch off sources and we just have two shock waves of different sizes. Like one is those shock waves in the future are going to bounce off the boundary and recollapse, and maybe they did something in the past. But why is that? That's a perfectly well-defined classical setup, right? Why is there a problem in that? It's just on one time slice. I'm just
saying there would be some co-dimension one surface on which you could distinguish those two solutions. In this case, it would be the boundary surface where you, like, that the other shock wave would hit the boundary at a different time or something like that.
Very good, very good. But here the information lives on a codimension 2 surface. You see, in a sense, you might have said that in any non-gravitational theory, the information always lives on a codimension 1 surface. That's not so surprising because we specify the state on a codimension 1 surface, right? You specify it in a time slice. So the interesting thing here is that it's actually codimension 2 that knows about all the data. I mean, I guess that's also true in ADS CFT, right?
Right.
So time slice, which is codimension
2. I don't disagree with the final statement that the information lives on a codimension 2 slice, which we know from ADS CFT.
Right.
But saying that we could have predicted it before knowing, ADS CFT is maybe too much. Like, which is what we are trying to say using these boundary unitarity arguments. We are trying to say, even if we didn't know about ADS CFT, we could have just thought of the classical Hamiltonian and so on and concluded.
But I didn't understand. The argument was not like this boundary unitarity argument of myself. I tried to make an argument using this, using these projectors on the vacuum. So there was a more precise argument I tried to make, which maybe I would. That's why I didn't. I don't want to confuse it with earlier arguments that were made in this. So I tried to make an independent argument using the projector on the vacuum and very well-defined assumptions. So. We could go through it, but that was the essence of the argument, was that if you assume that you can identify a unique state using the boundary Hamiltonian, then indeed you could have guessed that information lived in a codimension 2 surface. Just one more statement. It's actually not codimension 2 exactly for me because I also need the small thickness from 0 to epsilon. That was also important. So I'm not, but I don't need time from 0 to pi. I don't need light crossing time. I need time 0 to epsilon. In ADS-CFT, actually, you just say time 0. So from bulk arguments, I think you can argue that information is contained in a small strip, which can be very small.
Okay, maybe we should take this off.
Okay.
Yeah.
I have a question about the information paradox.
Yes.
So I usually think of it as if we sit at Scribe Plus as or the page curve rather, I usually think of this as a statement about a state in the Fock space of the gravitons and other massless particles. But I think you're not doing that. Like if we form a black hole and collect the first two Hawking quanta, you're not saying that those live in a pure state of the two particle Hilbert space, right?
Oh, no, certainly not. No.
But but that's what the page curve is referring to, that state. So
yeah, so you have to tell me what subset of the boundary algebra you're looking at. So the subset of the boundary algebra I was defining was where you take the Bondi mass and also the Bondi news operators. So the Bondi news operators are the ones that will measure what you said. And I was considering the algebra that you would get by taking all possible polynomials that include the Bondi mass and also the news. And then the claim is that the entanglement entropy has a trivial behavior. Now maybe your point is that you only want to measure the news and you don't want to measure the Bondi mass. You see, I mean, when you say you want to look at the Fock space, you have to, all I'm saying is that when you define the entanglement entropy, you have to tell me what is the algebra with respect to which the entanglement entropy is defined. So I mean, to say that we think of the Fock space, I think is not completely well defined. So Tom, does that?
Yeah, I think I understand what you're saying. You're saying that we can't really talk about, like, if we could talk about that Fock space, maybe it would be the page curve, but we can't really talk about that Fock space. But then won't we get into other problems? Like won't we not be able to even define an S matrix if we're not allowed to talk about asymptotic states in quantum gravity?
Let me say it another way. The thing that I'm allowed to measure are also, if you like, virtual fluctuations of these gravitons. So the question is, if you give me a state, and you might say that there are two gravitons have come out, but what that really means is that when you looked at the 1-point function of the news, that had some value, but then there are all these other high point functions that I want to look at, which are S-point functions of the real state is much more complicated. So it is a Fock space. I mean, in the asymptotic quantization picture, it is a Fock space, but the question is, what are the set of observables you're allowed to measure in the Fock space? And if you allow observables which are arbitrarily complicated, which include S-point correlators, including the Bondi mass and Bondi news, then you could identify which state you are in the Fock space. What you're saying is that you might have a situation where only two particles have physically come out of the Hawking radiation, and that's the statement that the 1-point function of the news has some profile. But I think what the point I was trying to make was that if you looked at arbitrarily high point functions in this Fock space, you would be able to determine just near the pass boundary of future null infinity which state in the Fock space you were in. It's a little bit like the setup I described here as well. Maybe I can go back to the ADS example, which is maybe this one. You see, you might have said that at T3 there are more particles which have come out, and at T2 no particles have come out. But the question I want to ask is, what is the precise restriction you're going to put on correlation functions that I'm allowed to measure at T2 and T3? You're completely right. If you look at 1-point functions of the metric, at T2 they're all 0, and at T3 they're not all 0 because some matter has actually come out. But I think these 1-point functions don't contain the information at T3. And if you look at very complicated correlators in both at T3 and at T2, they contain all the information. Does that answer the question?
I think so.
I think ADS is a good setup to look at. I mean, we have a small black hole that evaporates and that collapses and then evaporates. and then we compare how difficult it is to extract information at these two times. T2 when no Hawking radiation has come out, and T3 when all the Hawking radiation has come out. I mean, that's my cartoon on the left.
So you are saying there's a pure state in the Fox space.
There is a pure state in the Fox space, but to determine that it's a pure state, you have to measure arbitrarily high point correlators. If you only measure 2-point correlators, of course, it will look mixed. If you only measure 2-point functions, of course, it will look mixed. But if you measure arbitrarily high point functions, it will look pure. But that's true both at T2 and at T3. In that if you go to the time when all the Hawking radiation has come out and you measured only 2-point functions, your state would still look mixed. You would have to measure S-point functions to see the fact that the state was pure. But those S-point functions also contain the information earlier.
I think this is a little different than what happened in these recent ADS CFT examples. In that case, it's not a pure state in the Hilbert space of the CFT on whatever region you're looking at in the radiation, but it is a pure state if you include the boundary point.
Correct. It's different from that setup because in that setup, that setup was like this setup, for instance, right, where you had you have ADS and it goes to the bath, and the bath is not in a pure state. The bath is really in a mixed state. So if you have a setup where you have an exact factorization, then of course it's true that you will see a page curve emerge in the von Neumann entropy of the bath. Or alternately in this setup, I mean, I'm not disagreeing with the technical aspect of these results in that, you know, if you really switch off gravity in the middle, then it is true that on this red slice, you do not have a pure state earlier and later it becomes more and more pure. I mean, in this case, it saturates at some point. But I'm claiming that if you don't switch off gravity, then I claim that this is not the correct picture. And then I think the picture of the small black hole in ADS is more appropriate.
Okay, thank you.
So I'm not disagreeing with the technical aspect of these results. All I'm saying is that these results require a setup in which the Hilbert space really factorizes. And if you have gravity extending all the way out to null infinity, then that's not the case. And then I think the result is that the page curve is trivial.
I think just to comment, maybe another way of saying your point is that if you look at the same picture that you have drawn here, and you had gravity turned on at the endpoints of the intervals, then you'd have to apply the island rule to those points, and then you'd see that you'd want to connect the entire surface across the entire space-time and just get immediately a pure state. So the rules would be different, I think, as you say, even if you have very weakly coupled gravity.
Maybe. I'll have to think more about that, but maybe that's right. Yeah.
So I'm sure there's still many more questions and comments, but maybe in view of time, we can thank Suvrat again.
Thank you. Thank you very much, all of you, for sticking on for 1.5 hours. Thank you.